All right, guys. This is a few minutes after class. What I'm going to do here is I'll walk you through the rest of this problem. Um, so if we look at our velocity arrows, they're pointing to the left, which means they're negative values. Those negative values are getting smaller. So there's a couple ways we can go about this. If I compare my initial velocity to my ending velocity, so I want to know what my change in velocity is. So I have my initial velocity plus our change, which has been our happy little cloud or sad little cloud, depending on what your mood is, will equal our final velocity. So if I have -7 as my initial velocity and I add to it some number, I will eventually get -1 or 0 or whatever smaller negative value there you put in there. So this would mean I'd have a positive 6 meters per second, which means the positive here represents the direction of right. So my change in velocity is 6 meters per second to the right. Now this is one way of figuring out the direction of the change in velocity arrow. You can also say, all right, if I have a large arrow pointing to the left and eventually I get a small arrow pointing to the left, I needed to add an arrow pointing to the right to the initial to get the small final. Or if we look at our velocity versus time graph, if I have -7 meters per second on this graph, and I look at this graph over that 7 seconds, my acceleration here is a positive acceleration. All right, so you can use and this is what I mean by use the representations to help one versus the other. If you use the velocity versus time graph, which is a pretty straightforward graph to come up with, and you're unsure of the acceleration, you can say, oh, I have a positive slope here, which means my 1 meter per second should be positive. Or you can do it this way up here in the quarter, saying, I know my initial velocity. What do I have to add to my initial velocity to get my final velocity? So these are all different ways you can use the representations against each other to make sure they're consistent with each other. All right, now, another question that came up, which is going to be equally important, is what does the position versus time graph look like? So if we begin at 8 meters and we know this is traveling fast, this is going to start out with a large slope in the negative direction for the first part, so a large negative slope. As time goes on, it's still a negative velocity, which means the slope is going to diminish and become shallower. By the end of this, it's going to flatten out. So you're going to have a parabolic graph that looks like this at the end, because here the slope is 0, which means the velocity is 0. And here the velocity would be large at -7. This makes sense with this position directly underneath it on the velocity graph. And this is a large negative slope, which means you have a large negative velocity. So the slope gets shallower and still negative, and the numerical value for that also gets less and less negative. The acceleration is a constant positive acceleration. All right, so now we need to figure out the final position of when they come at rest. So if we take our equations and we look at what we're given and what we're looking for, we need to know the final position. There's a couple of things you can do right off the bat if you know the initial and final velocity. All right, we can use the v-squared equation. V-squared is equal to the original velocity plus 2a x minus x0. So we need to know what essentially our final position is. Our final position we substitute in 0. Well, actually simplify it first. So v squared minus v original squared divided by 2a is equal to x minus the original position. As I scroll down, well, too far down because I don't know what the numbers are. We're looking for our final position here. We know 8 is our initial position. I know my initial velocity is 0 minus a -7 squared. I don't know why that came out like a line, divided by an acceleration of 2 times 1 is equal to x minus, in this case, 8 meters. So we end up with -7 squared is 49, with the subtraction is -49 over 2 is equal to x minus 8 meters. Add 8 meters to both. All right, so 49 divided by 2 is -24.5, and you're adding 8 meters to it. So -24.5 plus 8 meters will give you a final position of -16.5 meters. So that would be your final position. You'd end up somewhere past the tree. Even though the motion diagram isn't perfect, it gives you a good idea of where you should end up. And that's how you guys go through this.